potential energy of an electric dipole in a uniform electric field. This is what we are going to discuss today. These parallel and equidistant lines are showing the electric field, and in that a dipole is being taken from infinity, from away about this electric field, and brought within this. Whatever we are going to do, that is mentioned as the work done, and we require energy for that. So this energy we want to find out now. If you look at this dipole, it is placed in the direction of electric field, one thing. And second thing is this, that the force applied on the minus q charge and plus q charge, that is equal in magnitude but opposite in direction. So no net force is there. But here this minus q charge of the dipole in comparison to this plus q charge has traveled extra distance too well, and because of this extra distance too well, there will be the net work done here. Now we are going to take it one by one. The work done in bringing a dipole from infinity to the point within the electric field is equal to the potential energy of a dipole in that electric field. Second thing, the electric dipole that has brought from infinity within the uniform electric field is such that the dipole movement is in the direction of the electric field, and while doing it, we know that minus q charge, it is clear that minus q charge is going to travel the extra distance too well in comparison to the plus q charge. So here the net work done by the system is equal to, work done is always equal to the force into the distance, and here the force will be experienced by the charge minus q, and extra distance it has traveled is 12. So putting these in the formula, we get work done equal to minus QE into 12. Here this can be written as minus PE, where P is the dipole moment and it is equal to the product of the charge and the distance. So we have got the work done is equal to dipole moment into the electric field. Now we have calculated the work done is equal to the product of the potential energy in the electric field according to the law of conservation of energy. What does it say? The law of conservation of energy mentions that whatever the work done here is stored in the form of potential energy. Work done is equal to potential energy of electric dipole. So one more thing comes out from here, that this movement, this work done, follows the law of conservation of energy, and it is denoted by U naught, that is equal to this work done only, so product of the electric field and the dipole moment. Now this potential energy, this potential energy U naught, this is in the stable equilibrium. Here this dipole is making an angle 0 degree with respect to the electric field. The potential energy U naught, where electric dipole is making an angle 0 degree with respect to the electric field, is said to be in stable equilibrium. Now, if the dipole is rotated at an angle theta, here it is in the direction of the electric field. When it is being rotated, a torque will be applied on it, and because of that torque, the work done will be equal to this relation. This is already I have found out in my last lecture, where we have found out the work done due to the rotation of the dipole in the uniform electric field. So I have taken here the direct result from there. So this is the work done when this is rotated at an angle theta, and the potential energy at this position theta is equal to U naught. U naught is the stable equilibrium potential energy that we have calculated right now, plus this additional work done, that is being given by so the potential energy at angle theta is given by product of the dipole moment, electric field, and the cos of angle between at which it is being rotated, or this can also be written as the dot product of these two quantities. Now, if this dipole is rotated at perpendicular direction, then angle will be the 90 degree. If dipole is rotated at 90 degree, that is theta is equal to 90 degree. Now cos 90 is 0, so the energy at theta equal to 90 degree in the perpendicular direction will be 0. So we conclude that no work is being done if this dipole is in perpendicular direction with respect to the electric field. Now, if the dipole is rotated at an angle 180 degree, it is just made in this opposite direction. If dipole is rotated at 180 degree, then the potential energy for this comes out to be minus P E cos 180, that is minus 1, or this is, so this is the maximum potential energy. At 180 degree experienced by electric dipole, and this is the position of unstable equilibrium and experiences unstable equilibrium. So we have discussed the two conditions. One is of stable equilibrium when the angle was 0, and unstable equilibrium, potential energy stored in the dipole is maximum but it is unstable here.